Thank you very much. It's an honor to be here, and so many great presentations this morning. I'm really pleased to be part of this. And in response to the last gentleman, Brennan, what I'll be talking about today would affect the interpretation I would want to make for those pseudo-REGs, rather than precognition of what the possible states of the pseudo-REG could be. I would want to suggest, the way I look at it would be a retroactive. I'm going to suggest that the collapse of that particular system into that particular state at that time is a relational process relative to you, the experimenter. And so therefore, it could be a process of retroactively affecting the actual time of the initiation of that pseudo-REG, rather than precognizing what it's going to be and then choosing that time in the present. So, and I think you could distinguish between those by running an experiment maybe modeled after Helmut Schmidt's work, because the data set is known in advance, right? Because it's generated by a mathematical function at time 0. The whole data set is known and can be analyzed in advance of the experiment being complete. So anyway, just some thoughts, and I'd love to talk with you, Brennan, later. Thank you for that great presentation. Is the red button the light? OK, great. So I'm going to talk about relational collapse. How many of you know what collapse of the wave function is in quantum mechanics, that concept? OK, how many of you know what relational collapse is? Relational collapse is the opposite of objective collapse. Objective collapse is the idea that a quantum mechanical system, given a plethora of multiple possible states, would take an objective single state as a result of a measurement by an individual. And that objective state has some kind of ontological status of being actually real for everybody, everywhere at that moment, rather than relational collapse, which means relative to the observer. So if you're familiar with Wigner's friend concept, that if Daniel makes an experimental measurement in the lab and I'm outside of the lab, when I enter the lab, the relational model would say that both Daniel and the experimental result are in a superposition state together, that they're correlated. But the actual reality of that result is not actually determined for me as the outside observer. And that is the relational model. Okay? So I'm going to use special relativity today to try and demonstrate to you that the relational model is the only viable interpretation of quantum mechanics that matches with special relativity, which is a pretty stringent criteria, because we know that special relativity is correct. So it's going to weed out about half of the interpretations of quantum mechanics, which is something that we have not been able to do yet. Currently, all interpretations of quantum mechanics are equally relevant. So hopefully I'll be able to demonstrate to you in a convincing way that that is the case. So the overview is that special relativity from 1905 leads to the conclusion that any definite reality must be described relative to another observer. This is called relationality. And the conclusion, at least my version of relationality, is that physical reality is secondary and consciousness is primary. I'm not the first one to talk about this. There's quite a bit of literature and ideas out there on this topic. And I'm going to try and show it rigorously that this has to be the case. So I'll start with the derivation. So many of the great advances in physics have been a result of people studying light. And all of these people have studied light as a major part of their careers. So we've got Einstein, Max Planck, Newton, Thomas Young, Maxwell, and Huygens. And we still don't know what light is, and that's the beauty of it. It's this central piece of physics that is still not understood. We've got lots of models, and all these models work very well for specific experiences, but there's stuff about light that is not understood. So let's talk about the Lorentz transformation for a simple non-light example. For muons, these are particles that are generated in the upper atmosphere. I'm going to try and use them to explain to you how special relativity works for those of you who might not be as familiar. And the main result we're going to talk about is time dilation. How many are familiar with the idea that time is dilated for objects in reference frames that are moving close to the speed of light, okay? Relative to me, the observer. So for a muon that's generated in the upper atmosphere by cosmic processes, a muon has a very short half-life of about 2 microseconds. So a muon is going to decay very quickly according to natural, spontaneous physical processes that I don't think we fully understand, or actually we probably do, but I'm not a particle physicist, so I don't understand them. But I know that after about 2 microseconds, they decay. And so it would look something like this. Okay? So what, in my model, I mean, this is just a metaphor, it's vibrating, wah, 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 poof, and explodes, right? That's my model for the decay of the muon. Wah, 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 wah. And what I'm trying to demonstrate here is that it has a certain process time. There's a certain physical process that's governing this behavior. And so what you would expect for a muon, even if it's traveling fast from the upper atmosphere, it's only 2 microseconds, so it doesn't get very far. And so this is what you would expect. It wouldn't get very far. It wouldn't make it to the surface of the Earth. And again, wah, 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 wah. Okay? But what actually happens is different. Because time is dilated for the process time of the muon, it looks like this. Wah, wah, wah. Okay? So what the process time is dilated, is actually slowed down from the reference frame of me sitting on the Earth. This is a basic result from special relativity that was confirmed in the 60s. And we observed many of these muons at the surface of the Earth, which indicates that, yes, indeed, time is dilated for these muons. Now, what's important here in this illustration is that I am talking about me as the observer on the surface of the Earth. I didn't put a clock in the reference frame of the muon. I didn't talk about the time as experienced by the muon, or the time relative to the reference frame of the muon. What I'm discussing is the time that I measure sitting on Earth. And what I'm measuring are 2 things. An Earth observer can measure 2 different time quantities. The first one is the amount of time it actually takes the muon to travel from the upper atmosphere to the lower atmosphere. That's from point A to point B. And I measure that on my stopwatch, and I write down the time that it takes. It might take a second for that to happen. That's the time for muon to get from A to B. The second thing I can measure, however, is the process time for the decay of the muon. And as we noted, the process time for the decay of the muon, it's obvious to us that it was dilated, because we know from other experiments that it takes 2 microseconds to decay. And in this experience, it lasted for much longer than that. And so we can infer that the process time of the muon has been dilated. The key point is that I am an earthbound observer, an inertial reference frame, making a measurement of this muon. And never once did I try and put myself in the reference frame of the muon, which is what we typically try to do in discussing relativity with yardsticks and stopwatches. In this case, those models of yardsticks and stopwatches are going to get in our way, because all I'm really doing is an earthbound observer making a measurement of these 2 time quantities relevant to the muon. So for a given time measured by me, less and less time passes for the muon from my point of view. Now here's my real point. What I'm about to say, for half of the physicists I talk to about this, they'll say, skip that whole part of your talk, it's obvious. That was what one physicist said to me at the end of the talk at the conference down in San Diego. And then the other half will say, I don't agree with that, that doesn't make any sense, it's meaningless. So I've decided that before moving on, I need to spend time figuring out how to present this in a way that is convincing and makes sense to people. So the point is that I can replace the muon with a light particle. Now what we're talking about is just a system that's moving at a given speed relative to me. The relative speed of the 2 systems. That's what Einstein talks about in his initial paper in 1905, is the relative speed of the 2 systems. He doesn't say inertial at all in that paper. And he doesn't talk about the reference frame. I mean, he talks about reference frame, I think, 1 time. And he talks about the relative speed of the 2 systems. And so it doesn't appear to me that there's any problem with talking about light. It's simply an entity that's moving past me at a certain speed. And that speed happens to be c, the speed of light. But I'm not putting myself in the quote-unquote reference frame of the photon. You can't do that. What I'm doing is measuring on Earth, from an earthbound position, the properties of this entity that's moving past me. So what we obtain, very obviously, from the equations of the Lorentz transformation is that the process time, or the time of evolution of the light, is equal to 0. So if I'm able to convince you of that, then the implications of that are very, very interesting. And we'll try and get there. So the implication to me is something like this. Light is timeless. We might also say time is meaningless. when we were discussing the process time of light. It's hard to talk about something that's meaningless, or it's hard to talk about timelessness from the perspective of you and I, who are in space and time, and that's how we do our physics. And that's why this is so hard to talk about in physics. But yet, I believe that we can show that it's an important conversation to have and that there are implications that can be measured. So possible objections are, light does not have a perspective. That's true. Light is not in an inertial reference frame. That's true. No clocks can move at light speed. That's true. And light cannot experience time. That's true. But I didn't say any of those things. Okay? And that's what I'm trying to get across. I'm working with a physicist right now, just talking weekly, and he's making sure I don't use words that point to any of these things. I'm not saying, what does light measure as its time frame, or what is the experience of light? How does light pass for time? None of those things make sense to talk about. What I'm saying is trying to define the process time for light that governs how it evolves, and saying that that value must be 0. And so light cannot evolve from point A to point B. It simply cannot. That's what the Lorentz Transformation says. For me, an earthbound observer, the light definitely changes. It goes from point A in the light bulb to point B on the clock on the wall to point C on my eyes. Those are 3 events that are separate in space and time for me, the observer. But to talk about that as those being separate events for the actual light doesn't make any sense, because light cannot evolve from point A to point B. A very quick technical point. These are what I would call origin-centered events. Light leaving the light bulb, traveling to the clock, and hitting the eyeball, call them A, B, and C. They all happen right where the light is. Let me show this video. So A, B, C. And for events like that, the distance between the events divided by the time taken between the events happens to be a special case where it's equal to the relative speed of the 2 systems, because those events are happening when the light actually arrives at those points. So this is a technical piece that allows us to make a modification to the Lorentz transformation. Here's a Lorentz transformation where t is the time measured by me for the light to move from point A to point B. L is the distance I measure for the light to go to point A to point B. And t prime is the process time of the light. This is what we're talking about as the process time of the light. And v is the relative speed of the 2 systems. When we plug in v equals L over t, this actually changes the equation from being one which becomes infinite to one which becomes 0. If it was infinite, it would be undefined and meaningless in physics. But in this case, instead of gamma on the left-hand side, you see gamma there. That usually blows up to infinity when you get to light speed. It actually cancels out with the term on top, and you get essentially t over gamma, or capital T times 1 minus v squared over c squared. And the reason I put this here is because it simply indicates that when you plug in v equals c at this point, you get a very nice, easy result, rather than anything that blows up to infinity. And so you get that the process time for the light equals to 0. Interpreting that is another matter and very challenging. So I've said light is timeless and light cannot evolve from point A to point B. And just a brief note, Einstein said that you could object that you can't plug v equals c into the Lorentz transform. You can't do that for an object that has mass, any kind of mass. But we're talking about light here specifically, and only light, which has no rest mass. And in Einstein's original paper, he said, for v equals c, all moving objects viewed from the stationary system shrivel up into plane figures, which is essentially what we're talking about here. For values greater than that of light, our deliberations become meaningless. But he doesn't say that for the value of light speed, our deliberations are meaningless. I think he would agree that it indicates that our deliberations become complicated, but not meaningless. And we have to understand that use case. They shrivel up into plane figures. What did that mean to him? What does that mean? So is it valid to ask how light registers events? We interact with light and make various distinguishable measurements that affect it. Light is an entity that gets changed by our measurements. So I do think it's valid to ask how light registers our interactions with it. And I don't have to say experiences our actions or anything like that. I'm saying registers is a very sort of physical word that doesn't have to do with anthropomorphism. So what is timelessness? How can light be timeless when we see it moving all the time? We can measure light moving from point A to point B very precisely. How can it be timeless? Well, the conclusion I draw from this is that light does not actually move. The Lorentz transformations say that space and time both become essentially zero, whatever that means. So light can't move. It has nowhere to go. It doesn't make any sense. It's undefined. The conclusion I draw is that light appears to have moved when it's measured. Light always appears to move a distance L in a time t given by the speed of light, but only when you make a measurement. You can't say anything about it other than that. And so when I observe light after bouncing off a clock on the wall, I'm observing it at a position in time as if it had traveled the intervening distance. That doesn't mean it actually did travel the intervening distance in some kind of continuous way or absolute real way. It means that it's measured to have done so when I actually make a measurement. And if you see some similarities to quantum mechanics, that's good, because we actually arrived at this without invoking quantum mechanics at all. The idea that the system doesn't have a definite state until a measurement is actually made is one of the central pieces of quantum mechanics, but we are just talking about special relativity at this point. And so to me, it brings them together in a way. It shows that they have a common origin or a common logic to them. If you plug in the t equals 0 in there, what you get is a very trivial result, which is that the distance and the time actually traveled by the light relative to me is given by the speed of light. So the light always appears to move at the speed of light. So here's the question I want to ask you. If light is timeless, then the now light already exists in tomorrow. So just take a minute to picture yourself on a sunny field. It's a beautiful sunny day, and you're feeling the warmth of the light on your skin. And that light is timeless. And so that very same light is connected timelessly somehow to when it left the event of the light leaving the sun 8 minutes before. It's also connected timelessly to the future. How can anything that's timeless not be connected to all of time in some regard? The light that we're experiencing in the future is connected timelessly to the light of today. It's hard to discuss it in physical words, but if you contemplate timelessness, this is the conclusion I've come to. The question is, which tomorrow is it connected to? If light is timeless, which tomorrow is it connected to? Is the future predetermined? It would seem that way. But I would say no. Light exists in all the possible futures. And so now we've landed on the conclusion that all these possible futures exist that light is timelessly connected to. And since light must always remain timeless, it can never objectively collapse to a single definite state. If light ever objectively took a definite state, then it would mean that I was changing the future of that light as well in some objective way, which doesn't make sense with the principle that light would be timeless. And so where I take that is the relational collapse model. The light only takes a definite state relative to me, the observer. And so any description is relative to an observer. So compatible interpretations that use this idea of relational collapse. Many worlds, many minds, consistent histories, relational, quantum Bayesianism, and decoherence theory. Decoherence is not really an interpretation, but it fits with this. Transactional, two-state vector formalism are both possibly compatible. I haven't figured it out yet. Incompatible interpretations, and this is where I think it's very interesting and relevant. The Penrose interpretation, anything involving objective reduction or objective collapse doesn't fit this model. GRW, the Copenhagen interpretation, simply said that macroscopic can't be separate from microscopic if you follow this model. That would imply some kind of objective reality that just can't be the case with special relativity. De Broglie-Bohm, von Neumann, and the von Neumann-Stapp interpretations. Although in discussion with Henry Stapp, I think we might have brought him a little closer to the relational view. So that's ongoing. A definite objective world out there does not need consciousness. But the relational world has a natural place for consciousness, the observer. So physical reality is secondary, takes definite form inside consciousness, and consciousness is primary.
Thank you very much. Thank you very much, Sky.
Thank you.
Quick question.
And just to mention, I have a book that will be coming out in December, and some experiments that are suggested for this, and I'd love any of you who would like to review it, I'd love to give you a copy.
Thanks, Sky. Your idea of the timelessness of light supports my idea of the symmetry of causality and retrocausality, and also Richard Shup's statement that causality has no real meaning, because what you have described, cause and effect, are coexistent and don't need to be separated. I think that's the point of what I'm trying to make.
So cause and effect become very problematic or interesting, I might say, if events that come, if to light, these events are not separate or distinct, A, B, and C, but to me, as an inertial observer, they are distinct. Causality is obviously true for me, but how does that work with something that's timeless and has all possible events, sort of is connected to all those possible events at the same time? I think it leads to conclusions. I think you can draw conclusions, but it takes a lot of deep thinking. And it doesn't, again, I'm not saying that there's no causality for us. For a human observer, we already know what the world does. The experiments are there, and we're following those. This is saying that there's some implications when you consider that light is timeless. But it's a great point.
Yeah, Sky, as you know, we've talked about this a bit from your last presentation last weekend. And I'm wondering what you've thought about the possibility that that which is spaceless and timeless, a primordial, non-existent void, would intersect dynamically with space-time, energy and matter, mind and body, however, quantum mechanically, classically, and be simultaneous in time and space, as evidenced by light as a timeless, possibly an arc discharge of some kind, interacting between the void and space-time.
Well, the reason I love studying this is because it's, in my view, profound and interesting and hard to form conclusions. I'd have to think about that some more. And I think that the idea of a void is very consistent with the idea of timelessness. They're both things that we cannot possibly describe with our current language and models. And so quite possibly similar descriptions of systems. Yeah, thanks.
In the observations of photons arriving on Earth that originated at the beginning of the universe, it says that as we observe those photons, we're not really looking at something that occurred in the past, but since the photons are timeless, we are literally looking at those events at the moment they happened.
Well, disregarding anything I've said, if blue light is emitted, if a pattern of blue and green light, say, is emitted from a star 100,000 years ago, that's 100,000 light years away, and we see it, and we see that pattern, we're seeing light as it was emitted. I mean, that we're seeing the event now, but we're making the assumption that it happened a long time ago, which I don't want to really call an assumption. I think the point that you're getting at is that light, it's absolutely rigorously true, I think, that light, because you can't consider it to have taken any particular time to get there, because light has dilated completely. I mean, the process time is 0. It does, in some sense, instantaneously connect the distant star and the observation of that distant star. But it takes a long time from an earthbound observer's reference frame for the light to make that distance. And in there is the dynamics that we're trying to uncover here.
Thank you. Thank you very much, Sky. We're running at least 20 minutes late, so I'm going to kind of cut off the questions, and I'll turn the mic over to Roger.
For 30 seconds.